Hello, everyone. My name is JonathanBrouse, and today I'll be showcasing my 909 capstone project, which is a custom geoprocessing tool I developed for the Pennsylvania State Police statewide radio network division. This tool automates LiDAR dataset retrieval and geodesic viewshed generation via a Python scripting tool in ArcGIS Pro. Some quick background: I am one of two analysts for the statewide radio network division for the Pennsylvania State Police, StarNet for short, and StarNet consists of over 250 microwave communication links and over 150 radio tower sites. StarNet is always evolving. Some of the radio tower sites and communication links are leased, and when a lease is expiring that cannot be renewed, we look for alternative sites to keep that link on the map. This requires the maintenance team to go out and remove the physical radio equipment from the tower and ground shelters. Before they can do that, my team needs to provide suggestions on where new viable sites are. This relocation workflow includes running a viewshed analysis from surrounding StarNet locations to determine a suitable relocation site. There are some small issues with the current workflow that could be improved. Anyone that has attempted to download data off of an interactive web viewer can attest that it is time-consuming, tedious, and the possibility of adding a few extra data sets into your selection is high. The workflow consists of testing multiple new locations for line of sight between multiple of our current sites. This process can eat up the better portion of a workday. When rerunning the analysis, it's always a possibility that your input parameters can be changed, resulting in inconsistent testing variables. So how can these issues be solved? By using a custom Python geoprocessing tool to automate the majority of the workflow. For this tool to work, it needs to create a polygon encapsulating the study area, select and download the LAS datasets automatically using that polygon, and then generate a viewshed raster from those LAS datasets. So let's talk about the datasets in question. This tool is designed to work with PAMAP LAS datasets. These are hosted datasets accessible through the Pennsylvania LiDAR Navigator, which is hosted by POSDA, the Pennsylvania Spatial Data Access open website that hosts authoritative data for the state of Pennsylvania. These PAMAP datasets cover the entire state, and they're broken into two separate datasets, north and south, as seen on the map on this slide. These datasets are subdivided into 10,000 by 10,000 US feet tiles. These tiles contain a download link in their attribute table for the LAS data that they represent. Now let's take a look at how the user interacts with this tool. There are 11 parameters the user must input into the GUI for the tool to run. It sounds like a lot, but what the tool asks you for is really simple information. The first 4 parameters ask for information about the observer and target locations. You specify the point feature classes that contain the observer or target, and then you use the paired SQL statements to select the specific record out of a feature containing numerous records. The SQL statements were a necessary addition because, as I mentioned earlier, StarNet's GIS layer contains over 150 sites, so this was an easy way to pick out the exact location we were trying to analyze. Continuing to the second half of the input parameters, the user must input the height above ground level where the observer is sitting. Since I'm dealing with radio towers, the antennas and dishes are around 150 to 250 feet off the ground, depending on that specific tower. The user will then input the desired area around the target location that will be included in the analysis. Sometimes R&D will request a specific plot of land, sometimes will be given the names of 2 intersecting roads, and they're interested in land up to 2 miles in any direction. This input allows the tool to have the flexibility in analyzing different area sizes. The user must then provide the REST URL for the hosted LAS tile layer from the Pennsylvania LiDAR Navigator. The user must also provide the name of the column that contains a URL to download the LiDAR dataset. The user can then specify the storage folder for the to-be-downloaded LAS datasets. This folder can be changed, but by default, the tool creates a storage folder in the project's home folder. The user can then designate the output name for the universal LAS dataset that is created after the tool merges all of the individually downloaded datasets into one. This name can also be changed, but the tool suggests a default naming convention. And then finally, this tool has a built-in rerun function. This allows the user to make edits to the LAS dataset in terms of removing or filtering out data errors and then rerunning the viewshed generation. So let's peek under the hood and see how this works. When the user hits run, the first thing the tool does is acquire the point geometry of the observer and target locations. It uses these point geometries to generate a line feature between these locations. This tool will then generate the buffer around the target location using the user's input parameter for the study area buffer size. This line feature is used to calculate a directional heading. Think in terms of a 360-degree compass. This directional heading is used as an input parameter for an upcoming process. Next, the study area buffer is run through the subdivide polygon tool and is split into 3 equal parts. When it's run through this tool, the compass directional heading that was calculated in the previous step is applied as an input parameter for the subdivide polygon tool. This rotational value, when applied to the subdivided polygon, ensures that the observer and target location's link line and the interior portions of the subdivided polygon meet at a 90-degree angle, as you can see in the photo on this slide. The tool selects and exports to a new feature the part of the subdivided polygon where the object ID is greater than 1. This creates 2 separate features representing the subdivided polygon. That object ID greater than 1 selection is then deleted from the original polygon. This process leaves the portion of the original subdivided polygon that is closest to the observer location. The vertexes of the original subdivided polygon, the purple polygon in this photo, are converted to point features. These point features are then run through a select by location query against the features that were exported to the new polygon, the yellow portions of the subdivided polygon in the photo of this slide. This selects the 2 points on the outer edges of the polygon near the middle. This point selection is then inverted so that every point but these 2 are selected and then deleted. So with those 2 point features left, they are combined with the observer point feature as inputs to create a closed line feature. This closed line feature is then converted into a polygon to create a triangular looking polygon. This triangular polygon is then clipped by the study area buffer to create that curved edge around the outside of the study area buffer. The study area buffer and this clipped triangular polygon are then run through the merge features tool. And this creates the conical polygon that is used to select the LAS datasets from the tile layer. And with that polygon created, the tool moves to select and download the LAS datasets. Using the REST URL provided in the GUI input, the tool adds that hosted layer to the project through ArcPy's add data from URL method. What appears is the black grid that you see in the photo. The tool then uses the conical polygon to run a select by location query to find the tiles that overlap the study area. From this selection, the tool uses a search cursor to retrieve the download URLs from the attribute field. It then appends these URLs to a new list. The tool then initiates a for loop to go through the previously created list. There are 4 if statements within this loop. The first if statement checks for an active download in your downloads folder by looking for a file with a certain extension. If that file and extension are present, the tool will print a message saying it's waiting for the file to finish downloading. It'll wait 5 seconds and then check again. When the file finishes downloading, it will move it to the storage folder that the user specified in the GUI and then unzip it. The second if statement checks if the zip file you need is already present in your storage folder. If the zip is there, it will check inside for an LAS file. If it finds the LAS file, it will unzip it and overwrite any matching files in the storage folder. If there's no LAS to be found in the zip file, the tool will delete that zip from the storage folder and start a new download to replace it. It will then go back to the beginning of the for loop and begin with checking for an active download. The third if statement checks if the zip you need is already present in your downloads folder. Similar code like the previous is executed if it's found and is or isn't missing the LAS file in the zip. The final if, or the else statement, simply initiates the download of the LAS dataset using Python's web browser package when no other conditions are met. The for loop will repeat these checks until the entire list of URLs has been run through. When all of the LAS datasets have been downloaded, they are merged into one universal dataset. This universal dataset is then converted into a raster, and this raster is run through the geodesic viewshed geoprocessing tool. The output and final step of the tool provides a symbolized raster layer. This raster layer has its symbology applied through the tool, where green is visible from the ground up to 80 feet, blue is visible from 80 feet to 120 feet, and clear is anything visible from 120 feet up. This symbology is what my team uses to determine a location's eligibility as a new connection for StarNet, but this symbology can be changed in the code if the user wants. Something I found while working with these LES datasets is that there tends to be some errors. As you can see in the picture on this slide, these errors can be pretty wacky. To solve this issue, I coded in that Boolean checkbox that allows a user to rerun the last few steps in the code. The user can make edits to the LES dataset, and then they can open up the tool from their history tab, check that rerun box, and then the tool will start running with the LASD being converted into a raster, and then the raster is reconverted into a viewshed. So what does this rerun look like? Here's an example of the pre and post use of the rerun feature. On the left, you can see the viewshed raster with streaks running through the layer and large chunks missing on the bottom areas. The picture on the previous slide is from this map's generation, and these data errors are what you're seeing on the map. To solve this, I imported the LAS dataset into a local scene and zoomed and panned around until I found those columns of data errors. I determined their class codes and then filtered them out in the layer properties. I then ran the LAS dataset back through the tool using the rerun feature, and the map on the right is the result that you get. Much cleaner looking. Moving on to some conclusions. The goals of the project were successfully met. The tool generates the conical polygon, which is necessary for the selection of the most necessary LAS datasets. The tool uses a REST URL to import a tile grid to automatically select LAS datasets, cutting down on unnecessary downloads and download times. And finally, the tool generates the viewshed raster from these datasets. Some developer notes: average completion time is between 15 minutes to a half hour, and these download times depend greatly on the distance between the target and observer locations. The longer the distance between the locations, the more datasets you'll need to download, and the longer the tool will take to complete. Another note is that in its current state, the tool is limited to hosted LAS datasets, accessible through a REST URL and with the download URLs for that LAS dataset in the grid's attribute table. Future improvements for the tool: I'd like to develop compatibility for more datasets. Since it's currently limited to the Pennsylvania LiDAR Navigator provided datasets, I think compatibility with the national map or USGS Earth Explorer would help to expand this tool's capabilities. I would also like to develop a more customizable download routine. Currently, the tool can only download to the Windows default C location. This tool will not work if the user has a modified downloads path. So, time check. Okay, I would like to do a quick tech demonstration to show you guys how the conical polygon gets generated. I will switch to my ArcGIS Pro. Can you all see my Pro project? Good. Okay, so as you can see, I have here in yellow an observer site sitting on top of this mountain, and I have two different target sites. I have here is the tool with all of the parameters already filled out, and you can see I use the SQL statements to pick the specific features that I want. So this tool will run faster than I can speak, so I'll do my best to keep up. When I hit run, the tool will grab the coordinates of the observer and target location. It will calculate that line between them, generate the study area buffer, and then calculate the linear directional mean. It will then subdivide that study area buffer, split it into two, convert the vertices to points. It will then make that triangular polygon between the point features and the observer target. It will then create the polygon, clip it, and then it will merge the study area and that clipped polygon into the conical polygon, which you can see here has been constructed. Now, to save time, I won't run the rest of the tool, but I do have here an example of these. This is the grid that will show when the LAS datasets have been selected, and then when the tool has finished running, this is the viewshed that will generate and show on screen. And with that, I'm going to switch back to my PowerPoint. And thank you. I will now take questions.